modify it because it was really finished. I would like to thank to the organizers of the conference for the financial support. And well, today I will talk about part of my recently finished PhD thesis, which is the implementation of this high-resolution spectroscopic technique in the search of disks and compact structures in planetary nebulae. Sorry. Okay, I will talk about the asymmetries, which is the main topic of this conference, and the observational challenges, beside the theoretical ones that they support. I will introduce the high-resolution spectroscopic technique. I will explain more or less how it works, and I will present the first preliminary results that we have obtained applying this technique to Cryonis data, and I will finish with a brief summary. Okay. As everybody here knows, if we want to deal with asymmetries, it will represent an observational challenge to observe, to detect, to resolve, to interpret, and to work with them. And we shall observe those AGB stars, protoplanetary nebulae, and geoplanetary nebulae. And these sources have in common that they may be obscured by dust, at least at the innermost regions, which are often really compact, and also they have molecular emission. So it makes complicated to observe, but fortunately they are strong infrared and radio emitters. In this context, interferometric studies have provided strong and clear evidences of equatorial structures, such as this green story. In the infrared VLTI may have some observational constraints regarding the baselines or the sensitivity, for example. In this context, we look toward another high-resolution technique, the spectroscopic technique, which has provided satisfactory results with standard instrumental setup and using one telescope. For example, it has been possible the detection of jets, neutron cores, disks around big stars, and the one that inspired us is this one. These people, this team have found protoplanetary quaternary radiation disks using Cryonis BLT data, and I just show you these plots of what they have found. So, how does this technique with this huge name work? Well, imagine that we are observing two sources. One of them is a point source, the other one is an asymmetric source, which is tilted respect to the plane of the sky, and one of the lobes is pointing toward us. Once we observe these sources with a ground-based telescope, we will have the signal blurred or smeared, and in the case of the asymmetric one, will appear as not resolved, more or less. We put the slit, and if we do it orientated in the major axis of symmetry, we will have the dispersed spectrum, and that's all that we need to start to work. Then the signatures or the spectroscopic signatures will be diluted or smeared, but we will perform a Gaussian fitting through the spatial axis, and we will cover the whole wavelength of interest, wavelength range of interest, and we will find the centroid of this emission, which is plotted here. And in the case of the point source, we will not detect any variation of the offsets, and it will not vary either at any position angle if it's a truly point source. But if it's asymmetric, we will start to see variation of the offsets, and then the original structure that was diluted in the continuum will appear. So, warning, all the techniques and all these things that we will talk about This technique has to be treated carefully as well. At least two position angles must be acquired to measure the variation of the spectrophotometric signatures. Also, the observation of an antiparallel or the complementary angle is mandatory to validate these signatures, because if it's an instrumental artifact, it will appear in the same orientation. If it's true, will be inverted, the signal. The lines of features that we aim to study will be selected considering the line to continuum ratio. If you have a low resolution spectrum, it's really good because you can see which lines or features are the most suitable for your study. If no long resolution spectra are available, you can use the chemistry or other things. Another thing that is really important is the continuum correction, because the signal of this, the emission of the line will be diluted with the continuum one. So you need to do something. You can subtract the continuum, or you can apply a correction factor using the flux of the line and the continuum. And another thing is that you really need a model fitting to interpret the data in the results that you obtain. So we have used Cryo's BOT commissioning data of two sources. One is a protoplanetary nebula, and the other one is a planetary nebula. We use it just to develop the methodology and the software to perform a spectrometric analysis. I want to say that neither of these sources was fully resolved in previous studies to know the morphological characteristics. So, the young planetary nebula SWSD1. Here is an HSD deconvolved image, and here I present the Krebs spectrum, the intensity of the line profiles, and the signatures that we have found. So we are resolving some structures on the iron 3 line and the bracket gamma line. As for the protoplanetary nebula IRAS 1751, we have here the Spitzer image, and we have the broad line of bracket gamma, single peaked line profile, and this structure that could be really suggestive. But again, warning, because these commissioning data have helped us to develop the methodology for the spectrometric analysis. But we have found suggesting a small size of the structure that goes from 12 milliards in the case of IRAS 7516, and in the case of SWSD1, up to 2,000 milliards. And that's all I want to talk about concerning to the commissioning data. But I would like to talk the red rectangle, this emblematic source that many of you know and some of you have worked with. What's going on the innermost regions of this peculiar source? We know that the red rectangle has a close binary common envelope progenitor. It has a dusty disk of crystalline silicates. It has been found the first Keplerian CO gaseous disk, and it has been proposed by means of the modeling of radiative transfer on the dust modeling that has a dusty, massive, and thick disk, likely operating at its innermost regions, but it has never been observed. So we have requested and observed the red rectangle. We have used the adaptive optics of Cryo's, which is available. We have observed the CO fundamental band at 4.9 microns, and we have observed 4 position angles and the respective antiparallel, just to validate the signatures that we aim to resolve. And here I present the preliminary results. So here is the first row is the spectrum as observed by Cryo's. The second row is the intensity of the line intensity profiles, and the third row the spectrometric results. So the first thing that I would like to say is that we have centered our analysis in the CO line of 4.9 microns, because we have detected another one, but we focus on So another thing that I would like to say is that we have detected double peak intensity line profile, which is a characteristic of Keplerian sources, and this is widely accepted, as Valentin Bujarabal said on his talk and works. Well, the other thing that I would like to note is the variation of the spectroscopic signatures along every position angle that we have studied. And for example, the one that is orientated along the minor axis has this antisymmetric position velocity field, which is also known as a characteristic of Keplerian sources. Here are the other, here are the antiparallel position, and I present them because I want to show you that these signatures are real. Originally were inverted, then we flipped just for the analysis, and we have again a consistent spectroscopic signature. And the stance goes from less than 10 milliseconds up to 50 or 60 milliseconds. Here I present a sketch just to figure out what we have found. But again, we don't have bond fitting. We cannot draw strong conclusions about this. But we have this, each of these is represent the position angle observed. And it's overclocked to an H-band image of Mexico, just to represent what's happening at the innermost region. So we have these blue and red dots. It represents the point of velocity, blue words and red words. And we don't know, maybe it can be this Keplerian toroidal structure of warmer CO gas along position angle 101. Well, what I really want to say is that more than in the interpretation of the data, because I cannot do that, I have not model fitting, I would like to emphasize on the size, because we are detecting a structure of 50 milliseconds or 35 astronomical units at this distance. And this is the thing that I would like you to take to home, that this technique may be helpful to resolve compact structures. In this case, we're talking about warmer material of CO. And I will finish with this conclusion. As I said, maybe it seems like this is a promising technique to find compact structures. Please look toward near infrared wavelengths where we have hotter material. We need bond fitting. We are preparing the spectroscopic analysis for Benson 3 and M29. And we plan to extend this work to a survey using CRIRES and VISIR to map as well the thermal dust. And we expect to find this and another compact structures. And we aim to complement the valuable information provided by the interferometers. And well, thank you.
I'm going to claim chairman's prerogative and ask two important questions. So can you go back to your slide showing the previous slide?
Continue.
Yes. So now on a large scale, there's this CO structure. Is it redshifted on the west and blue-shifted on the east? Good. Okay.
Yes.
And so does the velocity amplitude you see here coincide with the central mass that would be predicted by the large scale COs seen in the central location?
I'm sorry.
So you've got velocity amplitudes here that would tell you something about the central point mass around which perhaps this inner disk is rotating. Does it agree with the mass that you get from the CO at large?
I don't know. I haven't done this estimation. I just received this data in January, and I finished my master 2 weeks ago. So it's just a preliminary result. For this reason, I don't want to talk about interpretation, because I can't. I haven't made any model fitting, and I just want you to remember that we can resolve small structures, which is one of the main problems that the people has been talking about. So I can't tell you about this.
Fair enough. Yes, Valentin.
Which is the velocity separation between the peaks?
What?
The velocity separation between the peaks.
Okay,
The peaks in the spectrum.
In the spectrum.
Yeah, in the spectrum. It's less than 5 kilometers per second, I guess.
Something
Sorry,
like
I always
So
forget.
5 kilometers per second.
Well, the radial velocity that we have measured is less than 5 kilometers per second. And this one, I actually, sorry, I should, but yeah, it's few kilometers per second, maybe 10 or less. I'm sorry, I can't remember.
Well, with the velocity of about, for a rotation velocity of about, say, 4 kilometers per second, this is compatible with the rotation we see at large scale.
Yes,
So
we
it's
have
bigger.
less than 5 kilometers per second.
So
Yes.
something like 4 kilometers per second of rotation for the distance you have, I think it's compatible with the rest of the rotation.
That's
So
really
it would be
good.
the inner part, of the disk.
Yes, that's we think about. That's what we're thinking about. But we want to work more with this. And actually, I read all your papers and all the information. We choose this source because of this, because there's a lot of information. So our goal was to prove the capabilities of this technique. So it seems like we can show something interesting. So this work is in progress.
Thank you. Okay, we'll move on to the next talk then. Oh, did we give you your acknowledgement? Marcelo Leao Ferreira is going to tell us about magnetic